All right, how's it going, everybody? We are here on Monday, March 29th. Today we're going to be talking about section 7.8 as we get back into things here with week 10. We just had kind of 2 weeks where we didn't cover any new content, right? We had spring break week and we had our midterm week in there. But what we were doing right before we hit spring break was section 7.7, where we introduced solving some trig equations. Today we're going to look at trig equations part 2. We're going to solve some that are a little bit more challenging than the ones that we saw in 7.7. They're going to require us to do things like use our knowledge about quadratic equations as well as use some identities to kind of help us get there. So in a sense, 7.8 is nothing more than just an extension of 7.7. It's just more scenarios solving trig equations. The book is just nice enough to kind of break these up into two chunks. One where things are a little bit simpler, one where things are going to be a little bit harder out here. But I still think this will be pretty manageable here. We're just adding a Really, I think the tougher part here is we get more algebra steps. We're not getting any more trig here. We're just getting some algebra to be associated with our trig. In general, the equations that we solved in section 7.7, they were a bit simpler, and I'm putting that in quotes right there because I know that those were hard also, because those involved a single trig function in all those cases, right? We just had just a single like sine, cosine, or tangent and nothing else. So what we're going to see today is we're going to see some equations that involve things like both sines and cosines or something like that, and we're going to have to figure out how to deal with that. The other thing that we saw in previously in section 7.7 was that we only saw first powers of our trig functions, right? There wasn't any trig functions to a higher power, like a squared cosine or anything like that. But today we'll see some of that stuff in there, which is going to lend us towards some of these quadratic ideas that we're going to see associated with these guys. So it's sort of just, this isn't really like the two parts of solving trig equations are the quadratic and the not. But here in 7.8, what you're going to kind of see is that there's a chunk of topics that we want to talk about in how sometimes we can have trig equations being part of a quadratic type scenario where there's squared components. And so that'll be one of the things, one of the sort of groupings of examples that we'll look at today. That'll be about half of what we do. The other half of what we'll do won't necessarily directly be related to quadratics. It'll just be other types of kind of challenging situations right here. So today is one of those days where we just kind of want to like in this video, my goal is to kind of like help you develop intuition as to say to your, so that you can say to yourself, what should I be doing in any of these given scenarios here? These are all like a little bit less obvious than the ones in 7.7. And again, I know that 7.7 was probably challenging. And that's definitely the case that these are typically some of the hardest sections in this whole class here. So today, in a sense, we're stepping it up a little bit. But if you're comfortable with some of the things that we did in 7.7, we're just going to build on that a little bit today. Add on to some other like extra layers of algebra on the outside here. So what we're going to start with here today are trig equations that are quadratic in form, which means the structure of these equations resembles that of a quadratic equation, but there's going to be trig components within it. So that means to us, we're going to need to use quadratic solving techniques to help us solve these trig equations. And so what I want to do before we kind of get started right here is that we're going to refresh ourselves with some algebra. So you can see the first three problems I'm looking for us to solve here today, first three equations I'm looking for us to solve here today. No trig, we just want to remind ourselves algebraically what do we do to solve these types of equations here. Then we'll go on and we'll look at some equations that are quadratic in form, but officially trig equations. So in this next example, you can see the fourth one we'll look at today. You can see here, this looks like a quadratic equation because we have a squared term, a first power term, and then a constant term, right? So that looks like a quadratic, except that instead of just having something like the variable x, we have as our variable term sine of theta in this case right here. So this is sort of mixing together our trig ideas with our quadratic ideas from algebra, right? So this is kind of where we're headed. So let's go ahead and refresh ourselves on some algebra. I left myself a little gap right here because there's a couple algebra things I think that we should mention first. One is let's kind of state a couple things about our quadratics. So first of all, standard form of a quadratic. In general, standard form is when we write quadratics that look like this: ax squared plus bx plus c being equal to hopefully 0 is a very, very convenient thing for us. I'm going to state why in this little space over here in 1 second. But we can solve using the quadratic formula anything that's in this form. This is one way to solve a quadratic, is to use the quadratic formula here, which is going to tell us that if we have a quadratic expression, ax squared plus bx plus c, and if that expression is equal to 0, then we can solve for the values that what values of x make this equation true are going to be x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a, right? So the quadratic formula, something that'll probably come up for your use here in this section. So remind yourself of that. If you need to look that back up to use it, that's fine. But we should know when to use that. If we have a standard form quadratic, and very importantly, needing it to be equal to 0, then we can use the quadratic formula to solve, right? Another thing that we should remember here is we should remember that we might end up in a factored form rather than standard form, right? This is in factored form right here. We have the factor of x minus 2 and the factor of 5x plus 3. And so also remember our zero product property. I believe that we talked about this one in 7.7. Which says if we have some scenario like a times b equals 0, then a equals 0 or b equals 0, or both, right? This says if you ever multiply together two numbers and your output is 0, it has to be the case that one of the numbers or both of the numbers were 0. There's no other way anything else could happen. What that kind of says to me is that 0 is a very, very special number for us to be equal to if all we're doing on the other side of the equal sign is just a bunch of multiplication. And that's exactly what I see right here. So in our first algebra example, it looks like this guy right here, I could FOIL this out. I could multiply this out and get into a quadratic in standard form. But that seems like some work to me, and then I'd have to go use my quadratic formula. Instead, since this is already in factored form, I think it's going to be much, much simpler for us to use the zero product property to solve this equation here, because I do have what I would think of as this being my A term and this being my B term here, according to my zero product property. And so let's go ahead and solve, so again, just to kind of state what I was saying up here, these are in general our two most convenient ways to solve a quadratic equation. Either we need to get into factored form, like this example is right here, and then use the zero product property. That requires us typically to be able to factor. Whether we can do that or not is kind of one of the algebra skills that's up in the air for today. The other option here is if we are in standard form, if it looks like ax squared plus bx plus c like our second example does, then in this case, we can go ahead and use the quadratic formula to identify the solutions to that equation. So I'm going to do a couple both ways here because we want to see that we're going to get similar components for these guys. But kind of just these are kind of my two primary things I need to know about solving quadratics right here. Quadratic formula for standard form. But maybe easier if we can factor it, get into factored form so it looks like a number times a number like our first example, then the zero product property is typically easier, but doing the factoring step might be harder. Applying the zero product property, though, much easier than using the quadratic formula. So we'll see some pros and cons here. So let's go ahead and solve these guys right here. So in our first example here, what I'm very first identifying is this looks like a factored form because I have the factor of x minus 2 and the factor of 5x plus 3. Incredibly importantly, this is equal to 0. If this were equal to literally any other number, I would not be able to just solve this directly right now. I'd have to multiply the whole thing out, group that other number on the other side of the equal sign in with these terms here, then probably use the quadratic formula. Being equal to 0 is your best friend when it comes to solving anything that has any quadratic looking components here. So this is my best case scenario on the other side of the equal sign here. The zero product property is going to say, listen, if you multiplied a times b and got 0, then it must be the case that either a is equal to 0, which says to me x minus 2 is equal to 0, or it must be the case that 5x plus 3 is equal to 0. Those are the only two things that could possibly happen to result in getting 0 on the other side. This now gives me two individual equations that are very simple for me to solve algebraically right here. So to solve the first, all I got to do is add 2 to both sides, and I arrive at the solution of x equals 2. That's one of our solutions. The other one here, I've got to do at least 2 algebra steps here. I'm going to subtract 3 from both sides, and I'll divide both sides by 5. And so it looks like negative 3/5 is our other solution here. So it looks like this equation, because this was a quadratic equation, notice again, if we would have multiplied this thing out, we would have had x times 5x, which would have given us a 5x squared. And so since we had a power 2 equation, then that means that we should be expecting as many as up to 2 solutions. And we did get 2 solutions for this guy right here. We'll see some later today where we're not necessarily going to get that many solutions here, but we'll get to this, right? So this was really convenient. This was an equation given to us in one of our best case scenario formats. It was already factored for us. It was equal to 0. That's like your best case scenario on these guys. We won't necessarily expect to see that many that are that simple today, but this is a scenario in which we certainly should be able to solve. Now, looking at our second guy over here, we got to do a little bit more work for this guy. The thing that I immediately recognize is that this is certainly in standard form right here. This looks to me like I can see my A value is 1, my B value is -7, my C value is -18. And so that says to me I can identify what my standard form terms look like here. Therefore, I can use the quadratic formula. But I don't know. Every time I think about using the quadratic formula, I'm like, man, this thing looks terrible right here. I don't necessarily want to use this if I don't have to. So one of my questions I always ask myself is, could I maybe factor this thing myself and then use the zero product property instead? And we'll give that a shot here as well. So I'm going to do this guy 2 different ways here. One thing that we could do is let's go ahead and use the quadratic formula to solve. Again, you should recognize that this is in a pretty nice format for us already. It's already cleanly in standard form on the left side. We're equal to 0, which is a requirement for the quadratic formula to be used on the right-hand side. We're in pretty good shape to just directly go into the quadratic formula here. So let's take a look and see what this looks like here. We are going to get the fact that x is going to be equal to the negative of b. And notice that b is -7. I kept the negative on there. So the negative of -7 is going to be +7 plus or minus the square root of b squared. That's going to be -7 squared minus 4 times a times c. That's what's underneath the square root, all divided by 2 times our a term, which is just 2 times 1. So let's go ahead and simplify this guy here and see what we end up with. 7 plus or minus the square root of, so 2 simplifications under here. -7 squared is +49. Realize that because we're always getting a squared term here, this b squared term right here, this term's always positive. Sometimes people make some positive negative mistakes right here. I don't care if your b term is positive or negative, you are squaring it and getting a positive number. Numbers that get squared become positive. Positive times positive is positive, negative times negative is positive. Our other term here, it looks like we're doing, notice here, there's 2 negatives. -4, nobody cares about multiplying by 1, times -18 is going to be a positive, what, 72? All divided by, and that's just 2 down there. Now, 49 plus 72 is going to give me 121. And I actually know what the square root of 121 is. Quick trip to your calculator is going to tell you that the square root of 121 is 11. And so, for me to wrap up my answer here, all I would like to do is evaluate both the positive and the negative term that's associated with this right here. Notice that plus or minus when we verbalize that right there. That's just a phrasing for us that says, listen, we're getting this whole entire gigantic expression. There's 2 solutions that we're really looking for here. One is where you'd use plus, the other is where you'd use minus. I just don't want to write out this whole dang thing 2 times, which is why we use this shorthand abbreviation, plus or minus. We're really indicating that there's 2 entire equations that look like this with only one difference between them, the change of sign right there. So now is the time where we want to actually evaluate both the plus and the minus routes on this guy right here. So one thing I could do is I could consider using the plus version of this right here. That's going to tell me that x is going to be equal to 7 plus 11 over 2, which is 18 over 2, which is going to be 9. The other route I could take with this guy is the minus route. 7 minus 11 is going to give me a -4 over 2. And that's going to give me -2 as my other solution here. So it looks like the 2 solutions I found by way of the quadratic formula were 9 and -2. As promised, I'd like to do this equation. I'd like to solve this equation a second time right here, and I want to do this maybe what I think is actually a little bit simpler right here, right? So I'm going to solve this a second way. Let me get a different color right here so I can make sure that these are distinguished from one another right here. And let's go ahead and do this a second time. So this worked, but I don't know. It's easy to make mistakes when you're doing this kind of stuff. That was kind of more math than I would maybe prefer to do here if I could avoid it otherwise. If instead we did x squared minus 7x minus 18 equal to 0, I could maybe say to myself, well, look, maybe I can factor this thing, get into a factored form like our first problem was, and then maybe I could find our solutions from there. So let's remind ourselves how we want to factor. In general, the way that I go about factoring things is I take my C term. 18 is my C term, or negative 18, I guess, is my C term. And so I'm going to take that 18, and I ignore the sign for right now. I kind of deal with that in my head rather than manually attaching it to things right here. And what I want to do is I want to come up with all the product pairs that I could use to multiply up to 18. So, for example, 1 and 18 is a product pair that gets me to 18. 2 and 9, 3 and 6, 4, no, 5, no, and 6 we've already seen on the other side. So these are the three ways I could multiply two integers together to get to 18. Now the question I want to ask myself is, if these are the things that multiply to give us 18, I also want to pick the pair that adds or subtracts to get me to 7. And so looking here, using 1 and 18, I can't do any addition or subtraction to get to 7, so that's not going to be it. 2 and 9, I can do some addition and subtraction to get to 7 with 2 and 9. So this seems to me to be a good choice right there. Um, Finally, 3 and 6, I can get to numbers like 3 and 9 by doing addition and subtraction here. Those aren't the ones that I'm looking for. So I'm recognizing that 2 and 9 have the features that they multiply to 18. They can add, subtract to get to 7. Now I just got to pick the signs that should go with these guys. So I'm going to set up my factored form now. I know that my factored form is going to look something like this. And I just got to pick the terms that are going to go there. Now I've decided that 2 and 9 are the two terms that I'm going to use. And now I just want to pick the signs for each of them. It looks like when I add together these two terms that we need to get to negative 7. So that suggests to me we should choose a negative for the 9, but a positive for a 2. Now negative 9 and positive 2 add to negative 7. They multiply to negative 18. That's how I know this is the appropriate factored form relative to this standard form. Now we're in really good shape to use the zero product property here by just saying x plus 2 is equal to 0, or x minus 9 is equal to 0. And this leads us very easily to the two solutions, x equals negative 2 and x equals positive 9. So you can see that our solutions clearly match regardless of which technique that we chose. I think that the factoring technique is easier if you're okay with factoring. If this is the first time you've ever seen anybody factor a quadratic, then I don't necessarily think that's going to be the easiest thing for you to be doing right here. But if you're comfortable doing a little bit of factoring, I definitely think my solution there in purple is the easier of the two routes to go. In general, the quadratic formula is something that sort of like always works, except for in the kind of large proportion of times that people end up making small execution errors with it, since there's a lot of like, like small computation that you got to do. And that's, I just see people make lots of tiny mistakes when using the quadratic formula. So in general, I never go to the quadratic formula unless I feel like I need to. I always try for solutions like factoring first, and then I go to the quadratic formula if I can't make that happen. So again, I would say this is our better of the two routes here, but going with the quadratic formula is no problem as long as you can do it correctly there, right? So let's do another one similar to the previous one where I'm going to do it once using the quadratic formula, looking at this guy down here at the bottom, and I'm also going to attempt a factoring once. However, you should notice in this example, this 6 out front right there is going to make factoring quite a bit more challenging for us here. We have to use a little bit of a different factoring technique for this guy. And so in this one, I think it might lend itself slightly better to doing the quadratic formula just because the factoring is a little bit more challenging for this example on bottom than this factoring was up here. I think this factoring is very simple. I think we can all do this. This one's a little bit harder right here. So let's go ahead and take a look. So as promised, it seems to me like this guy is going to be possible to deal with the quadratic formula where a is 6, b is negative 1, and c is negative 2. So let's go ahead and do our quadratic formula solution first, then we'll do our factoring solution second. And again, you definitely never have to do any of these two ways. I'm just trying to like kind of show you some of your options for solving these types of equations. And obviously take a moment to realize that, we haven't done any trig yet here. We're just looking at what is the algebra that might be end up being associated with the trig that we're going to do. Right? So, doing the quadratic formula here. Again, standard form equal to 0. We're in pretty nice format for ourselves here. So, x equals negative b, so that's positive 1, plus or minus square root of b squared minus 4 times a times c. Oh, stop with that flashing business right there. Gosh. All that's underneath the square root. All divided by 2 times a. That's going to be 2 times 6. So I want to simplify this as much as I can now. It looks like I'm getting underneath the square root here positive 1. Again, notice this is negative 4 times negative 2. That's going to be a positive number in there. And what are we really getting here? 4 times 6 is 24, times 2 is 48. So I'm getting a plus 48 underneath the square root there with that 1, all divided by 12, it looks like. And that's going to lead me to 1 plus or minus square root of 49 over 12. And it looks like now I've done as much as I can, so now it's time for me, oh, excuse me, sorry. I need to now say this is 1 plus or minus 7 over 12. Now I want to go ahead and evaluate that plus route versus the minus route right there. So if I were to use the plus in this solution right here, 1 plus 7 is going to give me 8 over 12, which I could simplify as 2 over 3. So that's one of my solutions here. The other route that we should take right here is the minus route. If I use the minus right here, 1 minus 7, that's going to give me negative 6 over 12. And that's going to give me negative 1/2 as my other solution right here. So using the quadratic formula, able to come up with two fractional solutions right here, 2/3 and negative 1/2. So let's go ahead and see this guy using our factoring technique instead. So this one, as promised, takes a little bit more work than the other, but we can get through this here. 6x squared minus x minus 2 equals 0. Now, here's the deal with this one. This 6 sitting out front is going to be the thing that makes this different, right? The reason that we were able to factor this first one so simply is because this was a 1x squared right there. That was what made this simple factoring right here. This 6 sitting out front is going to kind of make things a little bit more challenging because when we get our two factors right here, we're not just going to get x in a number and then x in a number. The 6 is going to have to be in there somewhere. Maybe it's a 1x times 6x, maybe it's a 2x times a 3x, stuff like that. So we actually have more terms to kind of work out for ourselves here. So here's how this works a little bit differently. In general, these use a technique that's referred to as the AC method, right? A little bit different than our simple factoring that we saw up above right there. So if I'm going to factor this guy, here's what my steps look like. I'm going to compute what is A times C. And in this case, A is 6, C is negative 2, really. Again, I typically like ignore the negatives and the positives, and I deal with that stuff once I'm writing out my factored form. So it's definitely the case that A is 6 and C is negative 2. I'm just going to treat this as like 6 and 2 and multiply them to get 12 right here. All right. I'm going to do the same thing as I did above, and I'm going to make my product pair list for 12. I'm going to get all the possible ways that we could multiply together two integers and arrive at 12. Again, similar to what I did up above, I know that these are the three ways that I could multiply two numbers to get 12. I'm still interested, just like with above, in finding the pair that will also get me addition or subtraction to negative 1, right? That's my middle term. My B term here is negative 1. So I'm looking down the list here and I'm seeing 1 and 12 can get me to numbers like 11 and 13. That's not negative 1, so that's no good. 2 and 6 can get me to numbers like 4 and 8 by doing addition subtraction. That's no good. But 3 and 4, it seems like I could arrive at the number negative 1 by doing some addition and subtraction with 3 and 4. So it looks like this is going to be my good choice right here. All right. So what I'm going to do now is, so notice that this kind of factoring and selection process was very similar to the above process up here, but I'm going to do something a little bit different with it now. Now what I want to do is I'm going to rewrite negative 1x using the numbers 3 and 4 as coefficients instead. So here's what this is going to look like. I'm always going to leave my first term alone, 6x squared. I want to rewrite negative 1 using 3 and 4. And I think the way that I can do that is something like 3 minus 4 gives me negative 1. But those are all those are all coefficients on x, right? So what I think I'm going to do right here is I'm going to say plus 3x minus 4x minus 2 equals 0. So notice that what I just did right there is I took what we knew about negative x and the product pair choice that we made, and I rewrote negative 1x as positive 3x minus 4x. And the reason I made that choice is because 3 times negative 4 is negative 12, which is what we got from A times C. I just didn't write the negative right there. Also, positive 3 and negative 4 add together to give us negative 1, which is our middle term right there. All right? So this is my sort of like decomposing my B term, my middle term right there, using our product pair choice. And what we're now going to recognize is that there are really two groups that go together really nicely right here that have some things in common that we can collectively factor from them. So now I'm going to use a technique called factoring by grouping. I'm going to look at the first two values as a group and the second two values as a group and factor out some things that are in common of just that group from those two terms. So in the first grouping here, I see 6x squared and 3x. And so I say to myself, is there any common multiple in each of these two numbers right here? And I'm completely ignoring these two terms over here for right now. What I can see here is that both of these have an x in them, so I can factor out an x. I can also see that 6 and 3 are both divisible by 3. So I think that 3x is something I can factor out from this guy right here. So I'm going to factor out 3x. Remember, factoring is like a division process. So I've divided out 3x from 6x squared. What's left over? Well, if you do 6x squared divided by 3x, I'm still left with a 2 for a constant, and I'm still left with one of my x's. So 2x. And then I did 3x divided by 3x. Well, that's just going to leave me with 1. So there's my first term factored right there. Now let's look at our second grouping of terms, the negative 4x and the minus 2. I'm asking myself, what's in common between these two? Well, notice that the first term has an x, but the second term does not. So there's no x's I can factor out from the second grouping right here. However, both of these do seem to have a constant in common. They both are negative, so I can factor out a negative, and they're both divisible by 2. 4 and 2 are both divisible by 2. So I'm thinking I can factor out a negative 2 from each of these terms here. And remember that factoring is a division process. So when I did negative 4x divided by negative 2, that left me with a 2x. When I did negative 2 divided by negative 2, that left me with a positive 1. All right? So I just did my factoring by grouping, and you should notice something really, really special just happened right here. The two remainder groups that were left over are identical. They're both exactly 2x plus 1. So now I can kind of think of this to myself as now I'm saying, okay, out of this first big old term here and this second big old term that are broken down by that minus sign right there, I'm saying, is there anything in common between them? And I'm saying, well, yeah, they both have a factor of 2x plus 1. So now I'm going to go ahead and factor out that common factor of 2x plus 1 from each grouping. And I'm going to say, what's left over from the first group when we've divided out 2x plus 1? And you should say, well, the 3x survived. From the second group, what's left over after we've factored out the 2x plus 1? Well, the negative 2 is the only thing that's remaining. If we took negative 2 times 2x plus 1 and divided it by 2x plus 1, all that remains is the negative 2. So what we've done now is we've managed to get ourselves into nice factored form right here, and importantly, factored form equal to 0, so the 0 product property applies. And so now to kind of finish this guy up, I can go ahead and set individually each of my factors equal to 0 and solve. So 2x plus 1 is equal to 0, or 3x minus 2 is equal to 0. Here, I can subtract 1 from both sides and then divide by 2 to get negative 1/2. Or, for the other equation, I can add 2 to both sides and then divide by 3 to land at 2/3. And you should clearly see here that our solutions match using either of these techniques available to us right here. So again, I think that this factoring technique here, quite a bit tougher right here. I certainly expect you guys to be able to do our simple quadratic factoring right here. These ones might be a little bit tougher, but notice that the quadratic formula handled it for us anyway right there. So recognize that in a lot of quadratic scenarios, you do have multiple options. You should be making sure that you are for sure comfortable with at least one of those options. I think it would be good if you're comfortable both with factoring as well as using the quadratic formula. But then again, I think for me to sort of like really expect both of those things of you is an expectation that maybe a little bit more belongs in the college algebra course that most of you guys will be taking as well. So look for more of this when you take college algebra, but certainly a little bit of comfortability with the quadratic formula and at least a little bit of comfortability with factoring is certainly important here. Definitely some comfortability with the concept of the 0 product property to solve already factored equations important right here. So these are some of our quadratic algebra techniques that we need to have for our trig stuff. So let's go ahead and get into the trig now. So what we want to recognize is that these trig equations look a whole lot like the quadratic equations that we've already been solving here. So if I'm solving this guy, sine squared of theta plus 7 sine theta plus 6 equals 0, this feels like a quadratic to me, but it just has some trig components in it, right? So here's the thing that I like to think to myself that I do for myself. I'm trying to do myself a favor is basically the point here. So here's the favor that I want to do for myself. What I can kind of tell is going to happen right now is that we're going to really have two different things that we need to contend with. We need to manage the fact that this is a quadratic equation, so I need to do a bunch of quadratic math. The other thing that we need to manage is that this is a trig equation, so I'm going to need to manage some trig math. What I don't want to have to do is try and handle both of those things at the same time, right? So in general, my strategy for this is often to force myself into only one of the two situations at once. So a very common thing that I'll do in this type of situation right here is make a little bit of a variable substitution that allows me to not have to think about one of the two issues here, where my two issues are trig and quadratic. I feel like I've got to solve a quadratic equation sort of first. And so what I'm going to do is I'm going to make my trig stuff wait. And the way that I'm going to do that is I'm just going to make up a new variable. And in fact, I could even just call it x. Let me get a different color in here since I've been using purple here. And I'm just going to call it x. And what do I want x to be? Well, I just want it to be whatever my trig component is so that I can rewrite this equation without any trig parts. So if I'm just going to let x be sine of theta, then I can rewrite this now as x squared plus 7x plus 6 equals 0. Right? From here, I can either use the quadratic formula or I can factor this expression to arrive at my solution. However, you should notice that that will just tell me what x is. Our goal is to solve for theta, not for x. So we'll still have one additional step that we want to follow through with on the other end out there, right? So in this case right here, I'm going to go ahead and I'm going to use the factoring technique right here. But you could certainly use the quadratic formula here, and it would take you to the correct solutions either way, all right? So what I'm thinking to myself is I want to factor this. I'm going to make my product pair list for 6. It's either 1 and 6 or 2 and 3. It doesn't look like 2 and 3 is going to do it for me here because 2 and 3, I can only add or subtract to get numbers like 1 and 5. We need to add or subtract to get to 7, so that's not going to do it. But 1 and 6, I can do my addition and subtraction to get to 7. So it looks to me, and by the way, notice that if every single term is positive in your quadratic, that means you're going to make a choice of all positive terms in your breakdown here for the factors. So it seems to me like we're going to arrive at x plus 1 times x plus 6. I can now see that when I FOIL this guy back out, we're going to get 1 times 6. That's going to give me 6 on the end. I can also see that we're going to get things like 1 times x is x plus 6 times x. 1x plus 6x is 7x for the middle term here, as well as x times x to give me x squared. So I think I'm pretty good with my factored form right here. And I can finish solving. I can finish the algebra component of this by saying x plus 1 equals 0. And x plus 6 is equal to 0, giving me the two x solutions of -1 and -6. Right? So what I now want to do is I want to take my substitution equation as well as my two solutions in x, and I'm going to bring it all back together now. Right? So notice what we did here. We were given an equation in theta, but I said this looks complicated and I don't want to manage a quadratic trig equation. So we made a variable substitution, my statement here in green, that said, listen, ignore the trig part about this problem for a second. Just deal with the quadraticness of it for right now. We're done dealing with the quadratic part of it. We've solved the quadratic equation. Now I need to come back and say, okay, really this was actually a trig equation to get started. Let's bring in that trig component that we sort of ditched off to the side earlier and finish solving the equation for theta, not just for x, right? So we have arrived at the solutions of x equals -1 and x equals -6. So what I would now like to do is undo the substitution that we've done. X is the same thing as sine of theta, and my goal was really to find theta, not to find x, right? So I'm now going to say sine of theta equals -1 and sine of theta equals -6. What we're interested in now is finally solving these values for theta, right? We found the related x values. I want to now bring those all the way back to the theta values that we're really interested in at the very beginning here. So this first one's not too bad right here. When I think of sine of theta equals -1, I'm picturing on my unit circle. I know that sine measures height on the unit circle. A height of -1 means that we're way down here at the bottom. And notice this is one of those values where there's only one solution on the unit circle right there, right? There's not like, in a lot of cases, we have like two symmetric solutions or something like that for sine equals some value. But when we had sine of theta being its minimum possible value, there's only that one solution down there at the bottom. This is at 3 pi halves, right? That's 0 radians, pi halves radians, pi radians, 3 pi halves radians right there. So it looks like our instructions are saying to us, state the general solutions in terms of k. So it looks like associated with this component right here, I'm getting that theta is going to be 3 pi halves. What's our next solution going to be? Well, we can take any number of additional laps that we want to get here, right? If we did an additional 2 pi radians of rotation, we would just land at a new value that's going to end up having the same sine values as this one did right here. So that says to me, I can go ahead and just do any number of additional rotations. K rotations of 2 pi units will just take us another lap around, and that works forwards or backwards, right? If k is negative, then we can get some backwards rotation as well. The other equation that we want to solve here is sine of theta equals -6. But I'm noticing here, sine of theta only ever outputs values from -1 to 1. So this is saying, what angle is going to give me a sine value of -6? Well, there aren't any. We need to have a number between -1 and +1 as our output from the sine function for there to be any solutions. So I'm going to say here, since sine theta always outputs values in the range -1 to 1. This equation. When I say this equation, meaning that guy right there, has no solutions. So that just means to me it didn't contribute at all to the trig solution component of this because there is no solution to this equation right here. This says when do we get to a height of -6 on the unit circle, and the lowest height that we get to on the unit circle is only -1. That's like looking at a line, a horizontal line down here and saying, where did that hit the circle? Well, it didn't anywhere. All right, that's too low of a value for sine of theta being equal to -6. And so therefore, this seems to be the only component to our answer. So remember, as we kind of said a moment ago, quadratic equations, since they are squared, a power of 2 emerges, that means that we can end up with with up to 2 solutions or 2 solution families when we get trig equations that have the 2 pi k thing going on right there. In this case right here, one of the 2 solutions that we did find in x turned out to not be associated with any solutions in theta because the associated x value was outside of the range of the sine function right there. But -1 is something that we get out from the sine function, and we can identify what angles are going to be associated with that. So the key strategy component of this was saying when you have to deal with both trig and quadratic things, deal with one at a time. The variable substitution that I made allowed me to ignore the trig part for a little bit while I dealt with the quadratic part. Once I was done dealing with the quadratic part over here, I then said, okay, now let's go back and handle the trig stuff that I pushed off to the side. There's a really important strategy component right here. Never forget that you are completely welcome to make up any variable that suits you at any time, as long as you're still ultimately answering the original question that was asked. This variable substitution took me farther away from being in terms of theta, but it put me in a simpler solving situation right here. So this is definitely helpful for me to make these variable substitutions here. So let's go ahead and take a look at the next one right here. I think this one's going to be a little bit tougher, but still very, very similar to what we just dealt with right here. So a couple observations I want to make. I kind of want to compare these two real quick here. So one thing I see a trig term squared. That's an indication to me that I might be thinking about some quadratic type stuff. However, a thing that I'm seeing here is that this is a sine and this is a cosine right here. So my immediate concern is it doesn't seem to me like I can do this type of variable substitution here, because if I did something like x equals sine theta, then that only helps me out with this one, but I've still got a cosine term. Conversely, if I made x equal to cosine theta, that would help me substitute this term, but maybe not this term here. So one of my issues with this one is I've got two different trig functions, and that's going to make things really hard for me. I'd like there to just be one trig function out here so that I can do a nice clean variable substitution to solve a quadratic. The other thing that's kind of bothering me about this one is I don't like the fact that I have terms on both sides of the equation. We are very much happier when we have quadratics that are equal to 0 here. So it seems to me like another thing I'm going to want at some point is to push all my terms over to one side so that the equation is equal to 0. That will both allow me to do factoring or to use the quadratic formula, whatever route I choose to take on this problem right here. So what are we going to do here? Well, one of my issues that I pointed out to you is I really don't like the fact that I have two different trig functions in here, a cosine and a sine squared. So one of my questions to you is there some trig identity that I could use to either turn cosine into sine or to convert sine squared into some expression in cosine? I either want to turn I want to turn cosine into sine or sine into cosine somehow. And importantly, I'm noticing that this term over here is a squared sine. This should be a big, let's call this a green flag right here to you that says, ooh, I think I know what to do with that one. Right? I'm remembering here my trig identity that says that sine squared plus cosine squared equals 1, and therefore sine squared equals 1 minus cosine squared. The reason why this seems like a good idea for me right here is because I can therefore replace sine squared with 1 minus cosine squared. This is good because this introduces a cosine squared, which partners up with the cosine. So now I think we're going to have a quadratic in terms of cosine, just like this was a quadratic over here in terms of sine, right? So this seems to me to be a good move. Anytime I see a squared trig term, I remember that I always have a Pythagorean identity that can swap that out for a different squared trig term right here. So since these were mixed and matched right here, the Pythagorean identity can get me all in terms of one trig term right here. So let's go ahead and kind of apply this idea here. So 3 cosine theta plus 3 equals 2. Oh my gosh, that flickering on and off has got to go. Let me click my mouse somewhere else. And so I'm replacing sine squared with 1 minus cosine squared. And be careful here. I've got to use these parentheses because 2 is multiplying the entire amount sine squared. So 2 needs to multiply the entire amount 1 minus cosine squared. So the good news is it looks like we have an equation that is quadratic in cosine. So I think that my next move should be, let's expand on the right over here. And let's get everything on one side so that I can start using some of my quadratic ideas here. All right, so I'm going to expand and shift all my terms over. So 3 cosine theta plus 3 equals 2 minus 2 cosine squared theta. I want to move both of these terms over to the left-hand side. So I'm going to add over my 2 cosine squared. The 3 cosine theta stays. And here I had a positive 3, but I'm going to subtract 2 from both sides to shift this term over. So I'm going to get a plus 1 is equal to 0. Right? So I just shifted over my terms on the right to my terms on the left. Now I'm in pretty good shape here. Now I clearly have a standard form quadratic in terms of cosine with everything written on one side. This is now, in a sense, back in the same boat that we were in the previous problem to get started right here. Right? Now, the thing that I'm noticing that's a bit of a bummer is that this 2 sitting out front right here is going to mean it's going to be a lot tougher for me to do my factoring. So maybe this is a good problem for us to go and use the quadratic formula. So I think that my next move here now, and again, sorry, I keep on scrolling at kind of the wrong time. Now that I'm in my nice standard form quadratic setting where I have a squared term, a first ordered term, and a constant equal to 0, but there's trig terms, now is my good time to make my variable substitution. So I'm going to go ahead and do my x equals sine theta from before is really going to be x equals cosine theta here. X equals cosine theta. And that's going to allow me to rewrite this as 2x squared plus 3x plus 1 is equal to 0. So it now seems, and again, mimicking my previous problem, I would now like to find the solutions in x for the quadratic. Once I've found those, I can then come back and use my substitution to undo that substitution to get back in terms of theta again here. I think this one's going to go nicely with the quadratic formula because factoring this guy's a little bit tougher than factoring the previous problem here. So let's go ahead and do that. X equals, it looks like we're going to get a negative 3 plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. That's 2 times 2 because a is 2 right there. Let's go ahead and simplify this and see what we get. 9 minus 8, that's pretty convenient, all over 4. X is going to be negative 3 plus or minus square root of 1 over 4. Well, that's just negative 3 plus or minus 1 over 4. And now if I take this on the plus route and on the minus route, what am I going to get? Well, if I do plus right here, negative 3 plus 1 is negative 2. So I'm going to get negative 1/2 as one of my solutions in X. If I do the minus route, negative 3 minus 1 is going to give me negative 4 over 4. And that's just equal to negative 1. And I'm writing these x's a second time right here because we're not interested in solving for x. We are interested in solving for theta. We're really, really, really close now, though. All right? Let me get myself a little more room here, and we will now combine these statements here. So we found x equals negative 1, x equals negative 1/2. Now use x equals cos theta to solve for theta. All right, and again, we're just going to state our general solutions here, I think is what I said. State the general solutions in terms of k for each. All right, so it looks like I'm just replacing x with cosine theta. So it looks like we're getting here cosine theta equals negative 1, and cosine theta equals negative 1/2 are the two collective equations that are going to provide for us all of the solutions associated with this equation. For my first one, and again, I always just base these on my unit circle diagrams here. Cosine measures the left-right location on the unit circle. So cosine being equal to negative 1 puts us right there, right? This is located at pi radians, right? That's going 180 degrees right there. And it looks like we could continue to arrive at new solutions over and over again by adding 2 pi to this. So it looks like I'm going to be getting here theta equals pi plus 2 pi k. This gives me all the solutions associated with the x equals negative 1 solution. Now for the x equals negative 1/2 solution, which we've undone the substitution to write as cosine theta equals negative 1/2, I can now ask myself, when is it on the unit circle? What angles result in us arriving at a location to the left by negative 1/2? So I'm thinking to myself, there's my left-right location is at negative 1/2. So that's going to show me that there's two different ways that this can happen right here. It looks like this is going to be my smaller angle, and this is going to be my bigger angle over here. So what I'm seeing is this seems to me to be like 1/6 off of that 90 degree right there. So I'm thinking to myself, 1/6, 2/6, 3/6, 4 pi sixths, which is 2 pi thirds. 5 pi sixths, 6 pi sixths, 6 pi sixths because that's just pi, 7 pi sixths, 8 pi sixths. So it looks like 8 pi sixths, that's also known as 4 pi thirds. These are the two locations that we have a cosine value of negative 1/2. Just as we've been saying, 2 pi thirds isn't the only one. I could do a whole nother lap around the circle and land here again, a whole nother lap and land here again, a whole nother lap and land here again. Or we could do those laps backwards, do the negative 2 pi additional rotations with them. So not just those two solutions, but all angles that are coterminal with them. So that's where we're getting these 2 pi k terms. So this is going to lead me to two different statements that we want to make here. Because it's often the case that our trig equations introduce two solutions. So here I'm going to get theta is going to be equal to 2 pi thirds plus 2 pi k, as well as theta equals 4 pi thirds plus 2 pi k. So these three statements here collectively represent all of the infinite number of angles that would satisfy that original trig equation that we started with way back up here, right? So remember, we used an identity first to convert everything into one trig function, just cosine. Then we used a variable substitution to say, okay, now let's ignore that this is a trig equation. Let's just solve the quadraticness of it. We solved the quadratic equation using the quadratic formula and found our two quadratic solutions, but those were in terms of x. We really wanted theta. So then we had to go and undo the substitution that we did. And now we were able to pretty simply solve for theta with these two statements right here. This stuff right here is just the stuff that we saw in section 7.7. This isn't the difficult part of this. The difficult part of this, I think, is dealing with the quadratic. I think the first kind of half of this problem right up here is more challenging. Once we get down to here, these are two trig equations that we can much more easily come up with our general solutions for over here, right? And remember, I literally can't do these without drawing my unit circle every time. I absolutely expect that you guys are doing a little unit circle sketch for literally every one of these. I can't do it without it. This is like a necessary thing for me here. So let's look at, I think this is, oh no, we got two more that are related to quadratic land here, and then we'll look at some things that are outside of quadratic land. So this next one here feels similar to me as the previous problem. Cosine squared of theta plus sine of theta equals 2. This feels similar to me to the previous problem in that we have sines and cosines mixed, which I don't really like. I want to be in terms of one trig function here. The other thing I don't like is that this 2 is sitting on the other side of the equal signs. I know that anytime I see that I'm solving an equation in trig land where quadratic stuff is involved, I really want everything on one side of the equation here. So the two things I think I want to do are make the same identity swap here for cosine, and I want to bring this 2 over to be with the other groups of terms over here. So let's do those two things. So I remember from the last one that cosine squared can be swapped out with a 1 minus sine squared plus sine theta, and I'll subtract this 2 over to the other sides that were equal to 0. Just kind of grouping up some terms here. It looks like I have a 1 minus 2 is going to give me a negative 1. And I don't know. I never like my squared term being negative ever, so I'm going to multiply the whole equation by negative 1 on both sides of the equation. This is nice and easy because multiplying 0 by negative 1 doesn't change it at all. So I multiplied through by a negative right there on both sides. 0 times negative 1 just remained 0 right there. So now we're in a nice comfortable quadratic setting right here. Let's do our usual moves. Let's go ahead and let x equals sine theta. Let's rewrite this only in terms of x. This is x squared minus x plus 1 equals 0. Now let's go ahead and take this guy over to the quadratic formula here. X should be equal to negative b. B is negative 1. So negative negative 1 is positive 1 plus or minus square root of b squared minus 4 times a times c all over 2a. Looks like we're getting 1 plus or minus the square root of 1 minus 4 over 2. And that's going to take me to 1 plus or minus the square root of negative 3. Well, that's not a defined quantity right here, right? What we know about square rooting is it's only acceptable to take the square root of a positive number, and square roots only spit out positive numbers, right? Every time you're dealing with square roots, positives are the only thing that's involved. Only positives go in, only positives come out. This is not a defined quantity. This is not a real number. It's certainly the case that in general in math, there are reasons why we still want to consider the imaginary number complex solutions that are associated with these. In fact, we're even going to talk about that in a few weeks here, but not today. If we're given a real valued problem, then we are interested in real valued solutions. And so I'm going to say here, there are no real solutions to this here. And so basically the deal is there's no real solutions in x. So therefore there's no real solutions in theta. So my final answer for this is that there's no solutions, right? This is an equation that does not have any any solutions to the equation right here. One of the ways that I can show that this is going to be the case is we can go check this guy out in Desmos right here. If I want to see if there's any solutions for this guy in Desmos, then what I can do is I can say, let's graph just the left-hand side of this. Oh, it's not going to let me highlight this because okay, yep, not going to let me highlight this. Just the left-hand side of the equation, and I want to find where is it the same as the right-hand side, just being equal to 2. So if I pop over to Desmos here, cosine squared plus sine, okay, so I can do here cosine squared of, I'll do x plus sine of x. And our question is, when is this equal to 2? I'm going to make this a y equals. I want to know when is this the same as 2. And what you can see is that the line y equals 2 never touches the curve cosine squared plus sine. And they never touch each other. So when are they the same? The answer is never. This red curve never ever gets up to the height of positive 2. It just keeps on doing that awkward little squiggle that it does below 2 for all time. It looks like the highest it ever gets is 1.25 is the maximum height it ever gets to. We were asking when does it get to a height of 2, and the answer is it never does. And so therefore there are no values in the way I've written it in Desmos here. I'd say there are no x values that get us there. Of course, that's really our theta in our original problem, but that's not really an issue right there. So the bottom line is we can see graphically that there's not going to be any real solutions for this guy right here. So just be aware, this is absolutely a possible outcome with any of our trig equation solving scenarios. It might be that you get stuff where it's just like, oh, this doesn't contribute any solutions overall. There are no solutions. We can't take square roots of a negative. Remember that we actually already saw this a little bit earlier today. We saw back right here. We saw right here that similarly speaking, when does the sine of theta curve reach a height of -6? Well, it's way below the curve. Here's sine of theta and here's -6 down there. They're never at the same place at the same time. And so that contributed no solution. So kind of be aware that there are these kind of no solution scenarios that it's possible for us to encounter here. So let's go ahead and take a look at this guy right here, and then we'll kind of move on to a different chunk of topics right here. Cosine of 2 theta plus 3 equals 5 cosine of 1 theta. So my immediate concern with this problem right here is, what's up with the fact that we've got a 2 theta in one place and a 1 theta in the other? You should notice that this is going to ruin our ability to state something like, oh, x equals cosine theta. Well, if I do x equals cosine theta, all that's going to get for me is just a replacement for this. But x equals cosine theta isn't going to do anything for me to replace this. So just like it's an issue for me when I have mixed trig functions, sine and cosine, it's also an issue for me when I have mixed arguments. An argument is like an input into a function. It's a math word right there. Our arguments don't match. We have an argument of 2 theta and an argument of 1 theta. That's a problem for me in a very similar way to the issue of our functions themselves not matching up here. So this is now where I'm saying to myself, okay, that 2 theta is really bothering me. Is there some way that I can rewrite cosine of 2 theta in terms of some other things that aren't going to bother me as much? And so what I'm hoping that you're saying right now is 2 things. One is, I'm hoping you're saying, well, yeah, because we covered our double angle identities. The other thing I'm assuming that you're saying right now is, but I don't remember what our double angle identity actually is. So this is where I'm going to go and look up my formula sheet. I don't remember what formula I want to use to swap it out here, but I know for a fact that there is some way that I can write this term differently. It's a double angle, right? Cosine of 2 theta. I know there's some identity floating around out there that allow me to rewrite it. I'm hoping that one of them will be something that would help me solve this, but I'm not 100% sure. So I'm just going to go look for it right now, right? So let's go ahead and bring up our formula sheet here. Where's my formula sheet? Oh, there it is. All right, so let's bring up our formula sheet here. So this is back to the back of our textbook right here. And remember, this PDF is in Canvas. If you don't have this, you can go snag this guy out of Canvas back from like week 7, week 8 maybe. And so I'm looking around now. Where's cosine of 2 theta on this thing? Well, I see our double angle formulas are right over here. And oh my gosh, we have 3 different choices of cosine of 2 theta equations that we could use right here. So which one do we want to use? Which one do we think is going to help us the most? Well, this first one here, cosine of 2 theta, or sorry, cosine of 2 theta equals cosine squared minus sine squared. This is good because it gets us back into just single thetas on the other side over here. But this is bad because this is introducing both cosines and sines. And now it's just sort of swapping out one problem for another. Now I've got cosine stuff and sine stuff together. I want one trig function and I want it to just be of 1 theta. Our second trig identity for cosine of 2 theta is 2 cosine squared theta minus 1. This seems great to me because all this is doing is replacing cosine of 2 theta with a cosine of 1 theta. It's squared, which is a bit of a bummer, but we know how to deal with that. I mean, that's just telling me we're probably going to have some quadratic stuff to do. Finally, cosine of 2 theta equals 1 minus 2 sine squared theta. Again, this doesn't seem like a great choice because I don't want to introduce sine stuff when I already have cosine stuff as part of my problem. So it seems to me like this identity right here is going to be, I think, the most convenient thing for me to use right here. And again, I want to say this to you again. I absolutely don't expect that you just have all these identities memorized. I absolutely do expect that any time for basically the rest of your math career that you ever see like tangent of 2 times an angle or something, you should be saying to yourself, you know what? If this is ever an issue for me that I have this term right here, I know that there's some identity out there I can use to kind of swap some terms out to get something new. And I expect you to know that you can look it up in the back of your textbook or in this PDF that I posted in Canvas here, right? So this isn't like you're supposed to have all these memorized. This is like you're supposed to say, ooh, I know there's an identity for that, and you can look it up. And that's all I'm doing here too. It's not like I just knew this. I have to go look this up in my table here and see what might I use, right? So this is still how I do this. This is how you're going to do this forever. You need to know what the general structures look like of your identities, and then you need to be able to look them up and use them. So let's go ahead and do that here. So it looks like the identity of interest to us, cosine of 2 theta, is 2 cosine squared of theta minus 1. So I'm going to use that identity here. So let me write down that identity to the side here. So double angle identity. Cosine of 2 theta. Oops, sorry, not writing over here. There we are. Writing a word. Cosine of 2 theta equals 2 cosine squared theta minus 1. All right, that was the identity that we just looked up in our table right there. Okay. So using this, let's go ahead and see if we can rewrite this thing in terms of something we can actually handle. So 2 cosine squared theta minus 1 plus 3 equals 5 cosine theta. Looks like I don't need those parentheses. I just put them in there because I was doing a substitution. As usual, for all of our quadratic solving stuff, we always want to be equal to 0. So that says I want to move this term over to the left-hand side here. So I'm looking at 2 cosine squared theta minus 5 cosine theta. And for our constants, I have a negative 1 and a positive 3. So that's going to give me a positive 2 there. It's going to be equal to 0. So it looks like we've managed to do this one here. I'm going to go ahead and do this. I think just for the sake of it, I'm going to factor this one. The quadratic formula would totally work right here. No problem with the quadratic formula. Just for the sake of like kind of showing you guys all the different routes that we can take with this one, I'm going to factor it. So I'm just going to say, let's factor it. The quadratic formula would work too. All right, so we want to make our usual variable substitution to get started. X equals cosine theta. This is going to give me 2x squared minus 5x plus 2 equals 0. I'm going to use the AC method because we have this coefficient of 2 out here, right? So this says to me A times C is going to be 2 times 2, which is 4. My product pair list for 4 is real easy. That's all it is. We are looking for one product pair that has a product of 4. Both of those have a product of 4. We're also looking for the pair that has a sum or difference that'll take us to 5. 2 and 2 can never get us to 5. That can get us to 0 and 4, so that's out. But 1 and 4 can get us to numbers like 3 and 5 with addition and subtraction, so that seems like it is in. So we now want to replace negative 5, and we want to sort of decompose negative 5 into two terms that are using 1 and 4. So it looks like I can choose what signs I want with these, positive or negative. It seems like we need both a negative 1 and a negative 4 if we're going to get to negative 5. So I'm going to now write this as 2x squared minus, uh, yeah, I think that's fine, minus x minus 4x plus 2 equals 0. So again, notice I've decomposed 5x into negative x and negative 4x based on my choice of from the AC method list over here. Now we can go ahead and do some factoring by grouping. I'm going to group these two things into their two groups. And in the first group, I say, well, what's common between both groups? And we can look at that and see, well, there's an x common to both groups. And if I divide an x out, sorry, there's an x common to both terms in the first group. If I divide out an x from both terms in the first group, I'm left with a 2x from the first one and a minus 1 from the second. For our second grouping here, what I can see is there's a common factor of 2. And I always hate when my leading term is negative, so I'm going to factor out a negative from this guy as well. So I'm going to divide out a negative 2 from each term in the second group here. If I do that, I'm noticing when I divide this term by negative 2, it leaves me with a positive 2x. When I divide positive 2 by negative 2, I get a negative 1, and that's equal to 0. And now the little magic thing that happens with the AC method, if you did it right, is that your two remainder groups are identical. And so now I can say out of the first term versus the second term, what do they have in common? And they both have in common a factor of 2x minus 1. What terms are left over? Well, the x is left over from the first group, and the minus 2 is what's left over from the second group. And so it seems like we are going to arrive here at the solutions of 2x minus 1 is equal to 0, and x minus 2 is equal to 0. This leads me to the x solutions of x equals 1/2 and x equals 2. So I've got my two x solutions. So let's go ahead and convert our x solutions back into our theta solutions here. So I'm going to take these guys over here, and I'm going to join them up with our x. X equals cosine theta. X equals 1/2. X equals 2. Those are the three equations that I have that I'm relating to one another. So this is going to tell me that cosine theta equals 1/2 and cosine of theta equals 2. And we want to solve these individually here, get our general solutions. And as you'll see, that will wrap up our quadratic related things here. If that's been a bit of a bear for you, then we're almost done here with the quadratic parts here. So when does cosine theta get to be the value of positive 1/2? Well, here is where I have an x value of positive 1/2. So what I'm seeing here is it looks like we're getting like a 60-degree and a negative 60-degree angle right here. I'm going to do these in terms of positive radian counts right here. So it looks like that is pi thirds right there, or 2 pi sixths. And if that's 1 pi third, then 2 pi thirds, 3 pi thirds, 4 pi thirds, 5 pi thirds seems to be the other. And that makes sense because this is really like negative 1 pi thirds. So that's like 1 pi third fewer than 2 pi. And if you take 1 pi third away from 2 pi, you're left with 5 pi thirds there. So it looks like this equation gives me the two solutions of theta equals pi thirds plus 2 pi k, because we could do any number of additional rotations and land at something coterminal with pi thirds, or with with the 5 pi thirds there. So we've got our general solution for this equation for the cosine of theta equals 1/2. The other one that we've got here is that we've got when does the value of cosine of theta become equal to 2? Well, this is another one of our problem spots right here, right? If this is the x value of 1, then this is like saying when does our unit circle hit this dashed line of x equals 2? And the answer is it doesn't. This has no solutions in theta. Right? X equals 2 wasn't wrong for us to get out at all here. It's just that cosine of theta equals 2 has no solution. So there's nothing contributed here to our theta solution. So it seems like these are going to be the only locations that we're going to be getting solutions to this equation right there. All right. So again, the big strategy thing that goes on here is the stuff that I've written in green. These variable substitutions are really, really, really helpful. If you have a problem that you're trying to solve that's very difficult for two reasons, then what's really important is that you find a way to eliminate one of the difficulties while you deal with the other. Once you're done dealing with one of the difficulties, then you go back and you deal with the one difficulty that you ignored. In all these cases here, we've made a variable substitution so that we can just deal with the quadratic. Once we're done dealing with the quadratic, we then go back and say, okay, Now, really, we cheated. We got rid of our trig terms. Let's bring those back in where they belong and finish up by solving just these simple trig equations that we have right here. This is why section 7.7 was important, is because a lot of our hard problems ultimately boil down to these sort of more direct trig equations that we're solving right here. Okay, so that wraps up our quadratic related trig equations for the day. Equations. What other scenarios might we encounter? Well, there's still some other, things that we want to, I don't know, pay attention to here that might be a little bit challenging. So let's go ahead and see a few more examples here today. But I think we've done the ones that are sort of the hardest. These are just ones where I want to be able to say to you, ooh, be careful with this one scenario right here. Ooh, remember that we have our identity sheet here, stuff like that. So let's go ahead and look at these next ones here. I'm changing up our instructions a little bit, by the way, on these. We've just been giving just the general solutions for the previous ones. For all the remaining ones, I believe, I'm going to ask that we also determine the particular solutions in a given interval. So let's do the dang thing here. So first equation, sine of theta times cosine of theta equals -1/2. You should notice right away this doesn't look anything like a quadratic. I don't have any squared terms. I don't have any addition, subtraction. We do have some kind of inconvenience for ourselves here, which is that we have a sine of theta times a cosine of theta. That seems to be, I don't know, that's again, that it's often difficult for me to manage this. Now, when there's two different trig functions. One thing that would be really nice in this problem, one thing that would make this problem a lot easier for me is if we were equal to 0. If we were equal to 0, then I could just directly go to the zero product property and say, okay, either sine of theta equals 0 or cosine of theta equals 0. Two really easy equations for me to state my general solutions for. We're going to get 0 and pi for sine. We're going to get pi halves and 3 pi halves for cosine. We'd be done. But we're not equal to 0, so we don't get the zero product property. So I'm a little stuck here, and I'm thinking to myself every time I get stuck, I'm like, man, I wish this equation looked different. And what you need to burn into your brain is that every time you wish an equation looked different, you have a whole sheet of ways to rewrite trig stuff. So my question to myself is there some other way for me to rewrite the expression sine of theta times cosine of theta? Are there any identities that we ever saw that had this term in it? Let's go look at our identity sheet. Over on my identity sheet here, I am just hunting for somewhere on here that I see sine of theta times cosine of theta. So let's go on the hunt together. Nothing, 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 nothing here. Here's some sine of theta times some cosine of theta. There's one right there. But that, I don't know if that's going to help me, right? Because if I wanted to subtract over this term right here to the other side, then all I'm doing is swapping out one version of sine times cosine for a different version of sine times cosine plus some other terms out there. It doesn't seem to be directly, technically that would be a doable swap right there, but it's not like improving my situation at all. So a bunch of these have some technically viable terms in here, but they're not helping me simplify this in any way. There's nothing with these tangent statements right here. So back up to the top, and the half angle ones, no sines times cosines, double angles. Ooh, there's one right there. I'm seeing a sine theta times a cosine theta here. And in fact, actually over here, by the way, I'm seeing that I'm getting some right here as well. I feel like these are the two places where I might go to for my sine of theta times cosine of theta. I think that this one is going to be the easiest one for me to use right here, but I do want to say that this one definitely will work out here. If you chose to use this identity to help you rewrite this problem, you will definitely be able to get to the end from there. These are the ones that are just going to take us in circles over here, so I'm going to avoid that because, again, to swap out one sine or sine times cosine would just give us another version of sine times cosine in the equation, so it wouldn't help us kind of eliminate any of our difficulty here. So again, the two places I'm seeing that are going to be more helpful are going to be that sine times cosine and this sine times cosine here. I'm going to go ahead and use this one, but if you wanted to use this one, you would definitely be able to make it there as well. So here's the double angle formula I think that I see that's relevant here. So notice we're looking at the right-hand side of this formula, sort of in a sense, the output from a double angle formula. And it looks like we're going to be able to replace our current sine times cosine with just a single trig function, sine of 2 theta. It's a little bit of a bummer that 2 is in there, but it's really convenient for us that it's a single trig function to a single power. That's good for us right there. Now you should notice that 2 right there is something a little bit that we're going to need to like manage a little bit for ourselves right here, but I think we can do that, right? So what I want to say here is I've identified that there seems to be a formula from our table that I think is going to help us. Our double angle formula here says sine of 2 theta equals 2 sine theta cos theta. However, I don't have 2 sine theta cosine theta. I only have 1 sine theta cosine theta. So there's 2 different things I could do to kind of like manage this for myself. One, I could multiply my, sorry, not over here in Word. There we go. So one, I could multiply my original equation by 2 on both sides so that it perfectly matches this format over here. Alternatively, I could divide by 2 on both sides over here so that we only have sine theta cosine theta equals 1/2 of sine 2 theta, and then make our substitution. Either way would be fine. So I think I'm going to go ahead and do the multiply everything by 2 way to make this agree with our double angle formula. It doesn't matter. Either way, you're going to get to the same place right here. So I'm going to multiply by 2 so that we match our double angle formula statement. So 2 sine theta cos theta equals, I'm multiplying by 2, so this is just going to be -1. Now, 2 sine theta cos theta, that's exactly the terms that we see from our double angle formula. So I'm going to be able to replace that with sine of 2 theta equals -1. Now I'm in a really good shape right here to solve, right? And now is where I'm going to make the same type of variable substitution that we've made in 7.7, a little bit different than the ones that we've been making here today. But again, I'm going to say to myself, I have 2 difficulties left. I need to deal with the trig function. I need to deal with the fact that it's actually 2 times theta on the inside, not 1 times theta. So this is where I'm going to make a variable substitution to kind of simplify my life a little bit right here. And I'm going to say, let's let x just be 2 theta right there, just to simplify things for myself a little bit. So now it looks to me like I'm really just dealing with sine of x equals -1, right? This is, again, I've simplified it by making a variable substitution so that I can keep solving, and then I'll go back and undo that substitution I just made. So now I can go to my unit circle and I can say, hey, unit circle, sine measures height. When do we get to this height of -1 down here? Well, I can see that that's going to be happening at 3 pi halves radians right there. So it seems to me like this is going to tell me the solution that x is going to be 3 pi halves plus 2 pi k. However, we are not solving for x. We are solving for theta. So now I would like to undo the variable substitution that I made and say, listen, we weren't really just solving sine of x equals -1. We were solving sine of 2 theta equals -1. So since x is the same thing as 2 theta, I'm going to replace x with 2 theta. And all I've got to do to solve for theta is divide everything by 2. So it looks like this is my good general solution. I am now interested in knowing what are all of my solutions that are going to fall in the interval from 0 to 2 pi. Well, it doesn't look like there's going to be too many of them here. It looks like if k is equal to 0, then we just get 3 pi fourths. If k is equal to 1, then we're going to get 3 pi fourths plus pi, also known as 3 pi fourths plus 4 pi fourths, which is going to give me 7 pi fourths. And if I go any further, then if k is 2, then we're adding 2 pi to 3 pi fourths, so we're clearly bigger than 2 pi. So that's going to be the end of my like little list right there. So it seems like this is my particular solutions within the given interval of interest from 0 to 2 pi right there. Right? So this is a great problem because this is one where we cannot directly solve it as it stands. I can't just move some terms around. I needed to use an identity to make this happen, and I did. This step right here of making the substitution is maybe a bare smidge overkill, but I always do that for myself to like kind of help myself. And again, the point here is anytime you have more than one thing that's challenging for you, You need to just deal with one of the challenging parts at a time. So as soon as you see that multiple of theta in the inside, you should be like, dang it, I wish that wasn't there. Make a variable substitution so it's not there, and then deal with it later, right? I'm sort of putting off that being an issue so I can just deal with the fact that this is the sine function right here. I do want to say here, by the way, as my last note, just to kind of fill up my notes here, could have used a product to sum identity. I just want to say that was possible right there. I think this identity was the easier of the two to use, but we did see that formula for sine of theta times cosine of theta, and I've done it that way also, and it definitely works out that way. This is just the identity I chose to use in this context right here. All right? So there's one good one right there. And again, this requires the use of an identity to solve. There's no way that I am aware of to solve this equation without using an identity. And so it matters that we stop and say to ourselves, if you feel like you're stuck, you probably are. And that's where your formula sheet is your best friend, where you can just scan your finger on down the rows, looking for expressions that you've got and saying, ooh, here's something that kind of looks like some things that I have. Maybe I can swap out some parts. And we did. So let's look at our next example here. This one's going to be a bit weirder than the ones that we've seen previously. Solve this trig equation, give all solutions in the interval 0 to 2 pi. Well, what's your issue with this equation right here? My issue with this equation is that we have some trig parts, but we have some not trig parts. That x is not part of any trig equation right there. Well, this is going to be a difficulty for us because right now we have one x that's trapped inside of a sine function. And I could get it out of that sine function by using some inverse sine. But if I used an inverse sine to get this x out, then this x is now going to be trapped inside of an inverse sine. So we're really stuck. Either we have an x inside of a sine function, or we have an x stuck inside of an inverse sine function. There's never going to be any way for both of them to be free of the trig functions and to be grouped together right there. All right. So I'm going to say, since this equation has both trig and non-trig x variables, we cannot directly solve. So this is one of those cases where it turns out it is literally not possible to exactly solve this equation right here. There is no technique that will give us an exact solution to this equation because we have mixed trig functions with non-trig functions associated with our variable. So in this case right here, the only thing that we can really do for ourselves is go ask technology to estimate some solutions for us. So what I'm going to do is I'm going to graph two equations, y equals 5 sine x plus x, and y equals 3, and we are going to find intersections in Desmos. I want to know, when do these two amounts become equal to one another? All right. So let's pop on over to Desmos. Let's graph them both and see where do those graphs touch each other. When are they the same thing? I want to know when they are the same. That's what equals means right there. All right. So let's pop over to Desmos and do this guy. 5 sine x plus x. 5 sine x plus x. Now, you guys actually saw some stuff like this on a homework before. It looks like it is a sine function, but that's following the line y equals x, right? Y equals x is a diagonal line. We just have a trig function, 5 sine x, that is doing its trig behavior along the line y equals x right there. So you guys have actually seen some of that action here before. Y equals 3 is our other equation of interest, and we can see here, it looks like there are some locations at which these are the same as one another. And so I'm identifying here that there are, let me zoom out a little bit here. Notice, by the way, Desmos is giving me 4 gray dots right here. One of them is just because Desmos likes to identify X and Y intercepts right here. This is not a location of intersection of the 2 curves, right? Those are these 3 dots that are right here. So let's identify these 3 guys here, and I'm just going to take a snip of this and throw it into our notes here. Guess I better grab the whole thing, right? All right, hang on. I'm gonna fix one tiny thing just for, it doesn't really matter, but just to make this look a little cleaner right there. Stick that y equals in there. Desmos is pretty nice about you not needing to literally write y equals, which is nice. So now let me get these back on here. There we go. Now I'll snip this guy. Okay. Boom. So what we are interested in is answering the question, what are the x values that correspond with these points of intersection right here? Because our equation said solve for x, and so the 3 x values that I see in this problem are, all right, now I've got to reconvince Microsoft Word that we are going to draw again. I promised Microsoft Word I'm going to do it. It looks like, oh, Microsoft Word, I promise, we're gonna do it. No matter what you want me to do right here or not, I'm gonna do it. I'm gonna write some stuff. I'll fight this fight with you. Am I legal again? Nope, nope, nope. We're not doing that. That's not the thing I'm asking you to do. Okay, am I allowed to type? I'm allowed to type. Am I allowed? Nope, not allowed to do that. Can I type here? Yes. Can I draw here? All of a sudden, yes. Miracle. Okay. Draw, draw. It looks like we're getting x is, and I should say here, I want to be very careful with this. I am not saying x is equal to these decimals. I am saying x is approximately equal to these decimals here. And what are the 3 x values that we're seeing? 0.519, 3.177, 5.71. And by the way, you should notice that this problem suggested that we give all solutions in the interval 0 to 2 pi. Well, it turns out those were all 3 of the solutions that there were. It wasn't like there was an infinite number of solutions and we just picked out some. There were only 3 solutions, and all of them happened to already be in that interval. So that interval didn't restrict us at all right there. All of them did naturally occur within the requested interval right there. So there we go. Boom, got our 3 approximate solutions. That is the absolute best that we can do in this problem. It's not like you guys just haven't taken enough math yet. There straight up is not a way to get exact solutions out of this equation, period. The best we can do is numerical approximations from technology here. So that's what we got to do in that case. So anytime you ever see mixed trig with non-trig, can't do it. And you've got to use technology to get some support there. Okay, I think we've got just 2 more to go here, and these are going to show us, actually both of these are going to have some light relation to quadratic stuff. We're just not using the quadratic formula or factoring to get there, but both of these will have a little bit of a relationship with that. So this example says solve the trig equation, give the general solution as well as all solutions in the interval from 0 to 2 pi, then check each solution. So what we're going to see in this guy right here is we're going to need to be a little bit careful for one of the algebra steps that we're going to do. So I'm seeing here sine plus cosine equals 1. Sine of theta plus cosine of theta equals 1. And the thing that's, I don't know, we got some real bummers with this equation right here. The things that I'm seeing that are bothering me are this. 1. We've got mixed sine stuff with cosine stuff, and it's being added together. I don't know what to do with sine plus cosine. What I'm thinking to myself, what I would ask you is, what does this look very close to? What does this almost look like that you recognize? And everybody should be able to answer this one here. What does this almost look like? That's something that you recognize that we've used dozens of times over the course of this semester. To me, this looks almost like our Pythagorean identity. So it looks so close to this. This is kind of my like poking hint with this one. And not like my hint from me to you, like the hint from the equation to me. Like the hint that the equation is sort of giving me as to what I might do with this one is saying, this almost looks like an identity that I know. Maybe I can try and force it to get all the rest of the way to that identity because I think it would help me simplify this a lot. If this sine were squared and if that cosine were squared, then this would just be a generally true statement for all values of theta, right? But we're going to get something a little different than that here. But I'm kind of noticing like, man, how nice. This is one of our nicest identities in that it takes two complicated terms, sine squared and cosine squared. And when you add them together, you just get one, which is like the simplest term ever. So this is a really good like condensing identity that takes complicated stuff and makes it easy. So I'm thinking to myself, what could I do to this equation to make it look maybe more like that identity? So this is going to say to me, this kind of like observation that I just made right here is saying to myself, maybe I should square both sides of this equation. So let's go ahead and do that. I'm going to square both sides. Now, notice that squaring on the right is trivial. It doesn't do anything. One squared is just going to be one. Squaring on the left, don't you dare square this individually on both sides. In fact, do I have? Oh, I got to bring it up right now. I can't just have this and not show it right here. Hang on. I've got the oh man, where's the image I'm looking for? Oh, I gotta find it. It's gonna be here somewhere. There it is. All right, so here's your vaguely friendly reminder right here. Um, there you go. Let's go ahead and we gotta make this thing just the right size. Here we go. Here's your reminder right here. Oh, I can tighten this up. Here we go. Let's remind ourselves that a plus b squared is not a squared plus b squared, as Robin suggested. It is in fact a squared plus 2ab plus b squared right there. And you know what? I'm just copying this thing and throwing it in here. This deserves to be part of our course notes right here. I'm bringing it in. Make that smaller. There we go. This is what you should be picturing whenever you go to try and square a quadratic to make sure that you don't do it incorrectly here. So there we go. It is now part of our course notes. Let me bring this guy up here. Oh, come on. Don't you go doing crazy things to me, Batman. Yeah, Microsoft Word. Thank you. Thank you. There we go. Boom. Now it's part of our action right here. Remember that when you square something out, you do not individually square terms. You cannot distribute a square across addition. We have to FOIL this thing out. And what that means to me is that there's going to be that cross product term, that 2ab that gets introduced here. So just following this format, oh man, it's not going to let me, I know it's not going to let me write again. There's nothing I can do to just, oh my gosh, it actually did it. So following Batman's good advice right here, we're going to get the first term squared. So that's going to be sine squared of theta plus 2 times the first term times the second term plus 2 times sine theta cos theta plus the last term squared. And that's just equal to 1. All right. Now, it's not even clear to me if this helped me yet, but I think it did. Because the thing that I'm seeing here is that sine squared and cosine squared, those are going to join up to just be 1, right? So I'm going to get 2 sine theta cos theta equals, or sorry, I skipped my plus 1 right there. Equals 1, right? I can subtract 1 from both sides. And hey, we're in pretty good shape right now. And in fact, we have a couple of good routes to a solution from this setting right here. I want to show you both because today's all about strategy. And then we'll do our last example and we'll call it a day. So one thing I could do is I could say to myself, hey, listen, 2 sine theta cosine theta, I remember this identity. This is my double angle identity. My double angle identity says that this is really just sine of 2 theta equals 0. I know that sine in general gets me my solutions at 0 and at pi. And so therefore, I'm going to be getting 2 theta equals 0 plus 2 pi k. Or rather, I should say, notice that we're going to get a solution at 0, then pi, then 2 pi, then 3 pi, then 4 pi, then 5 pi, then 6 pi. So we're actually just getting like all the, I'm going to move this over here. We're actually just getting all of the counts of pi, right? So we're getting 2 theta equals 0 plus 2 pi k, and 2 theta equals pi plus 2 pi k. Notice that that's actually giving us collectively 2 theta equals just pi k here, right? Because if I were to list all these out, I'm getting the left one gives me all my even multiples of pi. This one gives me all my odd multiples of pi. So therefore, we're just getting all multiples of pi right there. And so therefore, I can finally do my division here and say theta equals pi halves k. So that's one way that I could go ahead and get to that solution here. Alternatively, a different thing I think I could do right here is I could say to myself, well, I'm noticing that I could think of the zero product property for this guy right here. And that's going to allow me to say, and notice here, that's just because we have a number times a number times a number equals 0. When is 2 equal to 0? Never. When is sine theta equal to 0? Well, sometimes. When is cosine theta equal to 0? Also sometimes. Let's go ahead and take a look real quick. When is sine theta equal to 0? Well, here and here. So that's just going to give me theta equals, and it looks like 0 plus 2 pi k and pi plus 2 pi k. So that's just going to give me my pi k. And over here, when is cosine of theta going to be equal to 0? Well, cosine is our left-right amount, so it's going to be here, and it's going to be here. So notice that this is going to be giving me my theta equals, what do we got, pi halves plus, and notice here, pi halves plus pi plus pi plus pi plus pi. I think I could just say this is plus pi k right there. And notice this is going to give me all of my, this is like 1 pi half, 3 pi halves, 5 pi halves. So it's all my odd pi halves. This is giving me all my even pi halves because it's like 0 pi halves, 2 pi halves, 4 pi halves. So in total, these two are collectively coming together to give me my theta equals all of my pi halves multiples right there, right? So it looks like either way we would want to solve this thing to get to the end, we could still kind of get there. And collectively, this is then going to give me the theta values in 0 to 2 pi of 0, pi halves, pi, 3 pi halves, and that's it. Because I said 0 to 2 pi, including 0, but not including 2 pi right there. So it looks like there's two different routes that we could go to get to our solution here. Both of them got us to the exact same solutions. That was good. So either of those are good thoughts we could have had to finish up the problem right there. Either using the double angle formula right there and identity, or using the zero product property and ripping it up into two different groupings of solutions right there. Either route got us to the same answer right here. Theta is going to be pi halves k. Right? Let's go ahead and, oh wait, oh my gosh, I almost forgot the last thing. Oh my gosh, I almost did something crazy right there, which was to walk away from this problem. I didn't finish following the instructions. Then check each solution. So, do these solutions actually work? So remember, our original equation was sine of theta plus cosine of theta equals 1. When theta equals 0, we're going to get sine of 0 plus cosine of 0 equals 1. Sine of 0 is 0. Cosine of 0 is 1. That's equal to 1. That's all good. When theta is equal to pi halves, we're going to get sine of pi halves plus cosine of pi halves equals 1. When we evaluate this, I am seeing sine of pi halves, that's going to be 1. Cosine of pi halves is 0. That's equal to 1. Yeah, totally. That works. No problem there. Our next solution is theta equals pi. And this should suggest to me that sine of pi plus cosine of pi equals 1. Well, sine of pi is 0. Cosine of pi is negative 1 equals 1. That's not true. Negative 1 is not equal to 1. That doesn't seem like it works. What about 3 pi halves? Well, we got sine of 3 pi halves plus cosine of 3 pi halves equals 1. Well, sine of 3 pi halves is pointing straight down. That's going to give us negative 1. Cosine of 3 pi halves has no left-right amount, so that's 0. That's equal to positive 1? No, it's not. So what the heck just happened right here? It looks like these two were wrong, and it looks like these two were right. Why did this happen? Well, notice that we were really close, right? This said negative 1 equals positive 1. We were really close. Why did we get some slightly incorrect answers for this guy? Well, there's one algebra step that's really important that we did that we got to watch out for. Our very, very first step in here was squaring both sides of the equation. When we square both sides of an equation, we lose track of the fact that there might have been some mismatched signs because every time we square something, it turns everything into a positive number. So it might have been that we started with some negative quantity and some positive quantity, but then when we squared both sides, it became two positive quantities, which might look like they match, when really, in fact, from their original equation, they did not. Right? So here's the warning that goes along with this one. I'm going to say warning. If one of your algebra steps is square both sides, you must, that is a requirement, right? So what we did here is we introduced something that is referred to as extraneous solutions. They're solutions that you find in the process of solving that aren't actually solutions to the original equation. Sometimes those get introduced when squaring both sides is one of the algebra steps that you take, because squaring numbers causes you to lose information about what their original sign was, positive or negative, right? If I say to you, I squared a number and I got 9, what did I square? Well, you don't know if I squared 3 or negative 3. Both of those square to become 9, right? So we're losing track of a piece of sign information. When I say sign, I mean positive or negative. And you should notice over here, these weren't like crazy statements. This wasn't like 14 equals negative 6. It was a statement that was almost true. It was only off by the sign on the 1, right? It was a negative 1 instead of a positive 1, right? So when you see these extraneous solution mistakes, like these errors that crop up right here, it should always be that your checks are almost right. but that you're only off by a positive or a negative out there. That's very typical for your extraneous solution check. So this is just saying, if ever in your entire mathematical life you square both sides of an equation in a solving process, you have to then check your solutions, because squaring both sides of an equation can introduce incorrect solutions into your solution set. And so you need to, at the end, go and say, well, I found all these. Now I need to check which ones of them are actually correct. We plugged in all four of the one that we found, and we only found that two of them were actually correct relative to the original equation right there. So those are the only two that we should keep for our actual solutions right here. So you don't always have to go and plug in every single answer that you get. But every time you square both sides of an equation, you have to go and check your answers, because that can cause incorrect extraneous solutions that are outside of the true solution set to be found that aren't quite right. So squaring both sides is sort of a red flag, which is why I wrote all this stuff in red right here. If ever you square both sides, then you have to check your answers at the end, because it's likely that you've introduced some incorrect answers through no fault of your own. It's just something that's going to crop up because squaring causes us to lose a little bit of information about positives versus negatives. Okay. Let's go ahead and do one more example here. I promise this is our last one. It doesn't have anything too crazy in its in its solving process here. There's just one last bit of algebra that we haven't discussed yet today that does matter, and so we need to go ahead and see it in action one time here. So solve the trig equation, give the general solution, give all the solutions in 0 to 2 pi. So nothing's going to happen too crazy here. You should notice that while this is a squared cosine term, there's no other cosine term. So that means to me I don't really feel like I need to go and do a bunch of like quadratic style stuff, right? For example, if I had the equation x squared minus 9, I'm not going to necessarily like go factor this or anything. I'm just going to add 9 to the other side and take a square root. But now we're in exactly the situation I just verbalized one moment ago, where I would say to you, hey, listen, man, I squared something and I got 9. What did I square? You should say to me, well, you either squared 3 or negative 3. Either of those would work in this situation right here. So a lesson that we need to kind of take away from here is that we are always introducing a plus or minus whenever we are undoing a square right here. So it looks to me like this should be giving me plus or minus 3. Either of those would cause our original equation to be true here. We're going to get very, very similar action to that right here. We're going to need to introduce a plus or minus. This is why there's a plus or minus in the quadratic formula, is because of a square rooting step that was taken in there. So let's go ahead and do this. I'm trying to get theta all alone. So the 3's got to go, the 4's got to go, and the square has to go by way of a square root. Then we can get rid of the cosines. Let's do this step by step. First, I'm going to add 3 to both sides. Then I'm going to divide by 4. Now I'd like to take a square root, but I know, because I learned my lesson over here, that anytime I take a square root, I need to introduce a plus or minus to go along with that. So it seems like the cosine of theta could have been plus or minus the square root of 3/4. And by the way, that's plus or minus the square root of 3 over the square root of 4, which should be plus or minus root 3 over 2. Back to being numbers that we're comfortable with right here, right? So one way that I'm seeing I need to solve this is where cosine of theta equals positive square root of 3 over 2. Another thing I'm seeing is cosine of theta being equal to negative square root of 3 over 2. So let's go ahead and see this kind of like branch into two different equations right here, right? So let's go ahead and solve these two guys. Now, on my unit circle here, square root of 3 over 2, that should be my horizontal amount. I know that's larger than 1/2, so I'm pushing that dashed line a little bit more to the right there. And it seems to me like there should be these two solutions that we're going to get right here and right here. It seems to me like this is like positive 30 degrees and negative 30 degrees, or positive pi sixths and negative pi sixths. But rather than negative pi sixths, I'm going to list this as its positive version. If I add 2 pi to negative pi sixths, I'm going to get 11 pi sixths. You should notice if you go one additional pi sixth more than this, you get to 12 pi sixths, which is 2 pi, which is the same, which is coterminal with 0 right there. So it seems like these are going to be my two solutions that I get out of this branch right here. So this is like our branches of branches type of solution right here. We're getting theta equals pi sixths plus 2 pi k. We're also getting theta equals 11 pi sixths plus 2 pi k. And these are our two solutions associated with one of our two branches. Now we go ahead and we do this again, right? Now we say, all right, well, it could have actually been on the other side over there. We could have been doing negative 3 pi halves over there. And that would be giving us these two guys right here. Again, our reference angle here is this 30-degree angle between our angles and the x-axis here. So I'm thinking to myself, this is something like 1 pi thirds, 2 pi thirds, 3 pi thirds, 4 pi thirds, 5 pi thirds, 6 pi thirds, 7 pi thirds. Oh wait, sorry, sixths, not thirds right there. I was doing my correct counting but saying thirds when I meant sixth right there. 5 pi sixths and 7 pi sixths. There are two angles of interest here. And so it looks like this as well is going to introduce to us two general solutions here of theta equals 5 pi sixths plus 2 pi k, and theta equals 7 pi sixths plus 2 pi k. So this is a great example because it just shows how much things can kind of like branch. We know that when we solve trig equations, it's often the case that when we have a trig function equal to some value, that it's very typically the case that there are two symmetric solutions, and we got two symmetric solutions twice here. The other thing that we're seeing here is that when we apply a square root to a squared number, that introduces a plus or minus, which is also sort of like a branching into two different paths right here. So our first branching was the plus or minus, which created two trig equations. Then each of the two trig equations had their own two solutions each, giving us four total equations for our general solution right here. And this is a good one because this is one of those ones where, like, I don't know, as I explain it, I feel like most people are like, yeah, okay, I totally see why we got all that stuff right there. But obviously, this is one of those ones that's just a little bit tougher for you to kind of like come up with on your own right here. Without having like seen somebody kind of get all these solutions before. So there's my good general solution. As our very last thing for the day, we're also asked to get the solutions within 0 to 2 pi. So let's go ahead and see if we can snag all these here. So within 0 to 2 pi, we're getting theta is equal to, and I'll create my curly braces for my list right here. So I'm going to try and go smallest to biggest right here. And so I'm noticing the smallest is pi sixths, then 5 pi sixths, then 7 pi sixths, then 11 pi sixths, right? So these aren't ordered smallest to biggest, but I typically like to write my particular solutions that way. So it looks like the first ones are all with k is equal to 0. And so, oh wait, oh my gosh, oh my gosh. Did I skip a step? Oh wait, no, I didn't skip a step. No, I just wrote the problem. Okay, all right. I'm looking at my notes right here, and in my notes I had a 2 theta right here, which certainly we could do. We would end up dividing each of these guys by 2 right here. So whatever. Okay, we skipped one of the slightly exciting parts of this one right here. That's okay. Pi sixths, and then 5 pi sixths, and then 7 pi sixths, and then 11 pi sixths for our final one right there. All right, I wanted there to be one last cool part of this problem, but that's okay. So we would have got 8 solutions if we did the 2 being incorporated into that, but we only got 4 solutions instead. So this is a good last one right here. This just required just basic algebra skills. This didn't require a special trig technique. It didn't require special trig stuff. It didn't require really special algebra stuff except for use a plus or minus when you take a square root. Didn't require any special quadratic stuff. Didn't require technology, all these good things right here. This was sort of a direct solving problem, but complicated because our solution branched because of the squaring. Our solution branched because we often get 2 solutions from trig equations, our 2 symmetric solutions on either side of one of our axes, stuff like that we get so often. So really good problems here. I know this is a really long video today, but I also know, 7.7 and 7.8, I think it's an easy argument that they're probably the 2 hardest back-to-back sections in this class right here. I do think it's probably better for you guys to have more than you wanted rather than less than you wanted from me for these guys here. So I'm hoping that you found this stuff very, very useful here as a reference guide for you. This is a ton about strategizing right here. There absolutely is not any cut and dried, like do these 5 steps and you'll solve every trig equation. There's just no way to kind of make some general rule set like that. So it really matters that you guys develop intuition about general solving strategies here. I think that one of the biggest takeaways that we should be getting from today is the substitutions that I wrote in green all over the place here. There's 2 different types of substitutions that we did. One is that when we're in a quadratic situation, I deal with only the quadratic parts by making a substitution for the entire trig equation or trig expression, like sine of theta or cosine of theta. The other types of substitutions that I'll occasionally do is that when I'm down to a simple single trig equation right here with a single trig term, if there's a multiple on the inside, or even more, if that was like a 5 theta plus 3 or something, I would substitute out that inside part so I can just deal with undoing the trig equation itself, then go back to deal with whatever might have been slightly more difficult to manage than normal on the inside. Remember that you are allowed to create any variables that are useful to you as long as you get back into the original variable that the problem started with to state your solutions. You're free to do that. And I think that a lot of people are like, oh, I didn't know I was allowed to do that. Hey man, that's kind of a crazy thing to say. This is algebra. As long as it's legal, then you're allowed to do it. Whether or not it's helpful or not is really the question. And so it's up to you to decide when are these types of substitutions the useful thing for you to be doing. So realize that I know that this is a pretty hard section out there. You should be experiencing some version of a struggle with these. You should be trying lots of different things, and you should hit me up when you get stuck with some of these problems in my open math because you will, because they're hard. And so know that I know that, and that there's videos in my open math to help you. I covered a lot of problems here today, and you can use this video as well as the PDF to help you as well. Hit me up with questions if you got questions. You're going to hit some snags with these, and I hope that we can kind of work through these together. This is tough, but this is super important. As I've kind of said multiple times, this is like one of our most important things to take away from this entire class is solving trig equations. I'd say it's easily my number one or number two most important thing that you leave trig with. Is being able to solve trig equations. These are going to come up constantly in your calculus classes, so it matters that we can do this here today. Do good with these. Experience the struggle. Try and think big picture about lots of these things. Strategize well. Use your formula sheet. All of you should make sure that you have your reference in the back of the textbook and that you have this PDF that you've downloaded out of Canvas, where I threw it in Canvas so you can have an easier digital copy of this guy right here. Oh man, so many times. I have this in all three of my courses folders this semester because I use this trig sheet as much in Calc 2 and differential equations as I do in trigonometry. I constantly am bringing this up in other classes. You will need to use this as reference in the future. You should get comfortable using it as a reference now. So that's all I've got for you guys here for today. Tomorrow, we're done with Chapter 7. You shall breathe a little bit of a sigh of relief. Sections 8.1, 8.2, and 8.3, I think, are a little bit easier than some of the stuff we did in Chapter 7. I won't go so far as to call them easy, but I think they are easier than 7.7 and 7.8 were here. I think a lot of people generally really like 8.1, 8.2, 8.3. That's all we cover in Chapter 8. And so I will see you guys in the next video for Section 8.1, which will definitely be, and by the way, out of all the sections in Chapter 8, 8.1 is the easiest also. So this week, the bulk of your work is to get good with 7.8. 8.1, I think, should be taking you half the time or less as what you should be spending on 7.8 here. So good luck with these guys, and I will see you guys in the next video for Section 8.1. Have a good one, everybody.